We have concurrent programming. Oops. So what to say? You know, think about when you go to explain something to people. You go to give somebody directions as to how to do something, how to bake a cake, right? How to make brownies, how to cook dinner, right? You explain things sequentially. Do this first, then this second, then this third, then this fourth. A, then B, then C, then D, right? This is how we do everything. Sometimes it's necessary, right? If I'm giving you directions as to how to drive, you know, from here to Squirrel Hill, right? You can't go straight on Forbes simultaneously with going right onto Murray. You sort of have to go straight on Forbes until you get to Murray and then make a right. But sometimes, just because it's the way our brain works, when you're in a kitchen cooking, there are oftentimes several possible things you could do simultaneously. You could be mixing the solids, you could be mixing the liquids, right? You could be preparing the pan, or you could be preparing the batter, whatever it happens to be, right? But we still explain to people sequentially. You know, so what are you going to do? First, put the solids in a bowl, stir the solids. Put the liquids in another bowl, stir the liquids. Spray the pan, right? Because that's how our brains work. Our brains tend to naturally think sequentially. They didn't think sequentially when tasks are sequential. They think sequentially when there's a possibility that multiple things can happen at the same time, right? Imagine if you were in that kitchen and you were in a hurry, and everybody knew how to make a cake. Everybody already knew. And so one person said, okay, I'll take care of these, and somebody else said, I'll take care of this. Okay, I'll grab a pan, right? And now everybody started working together, right? You can imagine that cake could be made in parallel, right, with concurrency. One person working on the solids, one person working on the liquids, one person getting the pan greased and into the oven and whatever, right? But it's just not how we think about things. And so when we try to program concurrently in software, it gets hard. Because it's asking our brains to do something they don't do every day, right? But why would we want to program concurrently? Slide deck sort of missed that point, yeah. Yeah, the answer is doing more things at the same time is better than doing less things at the same time, right? More is better than less. So in some levels of concurrency, there's concurrency with respect to the processor. I want to keep all of my cores busy. I want to make sure that if I have 8 cores on my machine, all 8 cores are working toward my goals, to helping me accomplish what I want my program to accomplish, right? And there's also concurrency when it comes to different resources. I'd like to be in a situation where I'm simultaneously using my processor, my disk, and my memory, using all of the resources currently available to me, right? That's better than only using some of them. If I can use my processor, my memory, and my disk all at the same time, that's great. That's a lot better than using my processor and idling my memory and my disk, and then using my memory and idling my disk and my processor, and so on. Right? So the reason we want to be able to program it concurrently is to take advantage of the fact that a whole bunch of different resources exist at the same time. We can use those resources at the same time. We can get more work done at the same time. Trick, like I said, is being able to think concurrently and figure out how to do that. We've all heard of the joke about too many cooks in the kitchen, right? We don't want our code in that situation where everybody comes and adds their pinch of salt. Okay. The human mind tends to be sequential. The notion of time is often misleading, right? You can't really talk about first, second, and third if 2 things are happening at the same time. They're both first, right? If you ask how long did something take, and it took 2 people a half an hour to make that cake, does that mean one person will do it in an hour or 45 minutes? Or maybe they were getting in each other's way. It would take one person only 15. I've been in that day, right? So it's hard to understand what time means when instead of having one timeline and everything moves along that timeline, right, you have multiple timelines. Do we mean total time? Clock time? What are we talking about? And as soon as you have multiple things going on at the same time, right, synchronizing them becomes really hard. I'd hate to be in a situation where, I was making the cake batter, right, and I went to pour it into the bowl, or pour it into the pan, and the pan wasn't there yet. Oops. Right? So when we think about things, and multiple things are happening at the same time, right, we have to think about all the possible sequences of events and realize that there's a lot of opportunity for error there. Have any of you guys been on a group project with a bunch of people, and you planned it all out. I'm going to do this and have it ready Tuesday, and that person's then going to come in Wednesday, and they're going to take those two pieces and blah, 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 blah. Right? I'm going to work on this part of the project. My partner's going to work on this part of the project. Then we're going to have both of these on Tuesday. Then we're going to integrate them on Tuesday. And then on Wednesday, we're going to make the presentation. And I'm going to work on the slides, and she's going to work on the pictures. And then we're going to put the slides and the pictures together. And then on Thursday, we'll all practice or something, right? You put together this great plan. What invariably happens? You've been there. I can see the smile. It doesn't happen. Right? Somebody gets ahead. Somebody gets behind. Something goes wrong, right? It happens. Maybe not in your groups, but look, I remember on projects, my group of friends, right, everybody was motivated, excited, whatever, would rush ahead on a project, and then like I'd finish my part, so I'd start your part. Like that's somehow a help. Now you have two people doing that part. Now we've got to figure out which version we use. Great. Right, or how to put the pieces together. Right? Sometimes somebody falls behind. There are a lot of deadlines. People stay busy. And now we can't put things together because parts missing. Right? So it gets really hard. We have multiple resources, we have multiple things going on at the same time, getting them synced up. I don't want to know how they manage to park like that. I'd like to learn that trick. That would open up so much better parking. Okay. So at any rate, this situation, right, you can imagine, occurred because, three cars, were driving looking for parking spaces and saw the same two. One car picked the space on the left, one car picked the space on the right, and sadly one car, we don't know which space it picked, it got squeezed between the other two. Okay? Here's an example with the parking spaces and then two cars spotting the same one. It's called a race condition. Okay? A race condition is a situation where the outcome depends on timing. Who wins the race to certain points? What we see depends on which process gets here first. Okay? That's why they call it a race condition. So if you have multiple processes, multiple threads, whatever unit of concurrency happens to be, these things are proceeding along their own timeline, and the results as we, the users, see them simply depend on which process happens to get to which point first. Timing is everything. Deadlock. Deadlock is a situation where there are dependencies, and as a result of those dependencies, progress can never be made. Okay? Traditionally speaking, there are four necessary and sufficient conditions for deadlock. What does the word necessary mean? What's that? Has to happen, right? Okay. It's a necessary condition, a condition that has to happen. All right? And what does sufficient mean? Yeah, right? If dropping a match in gasoline is sufficient to start a fire, that means if you drop a match in gasoline, you're going to have a fire. Right? These conditions are necessary and sufficient. That means that you can't have deadlock without them, and if you have them, you're guaranteed to have deadlock. Does that make sense?
If and only if.
Necessary and sufficient. So because they're necessary, it can't occur without any one of them.
Yes, I'm saying it's if and only
It is if and only if, yes. Sorry, I thought there was a question. So yes, it is if and only if. Right? Because they're necessary, so it can't occur if any one of them is missing, and they're sufficient, so it's guaranteed if all of them are present. Okay? You have to have serially reusable resources. What does this mean? This means that if we're talking about deadlock, we have to be talking about a situation where we have a resource, like a toilet, that can be used by one person at a time. Okay? But gets reused from person to person. It's serially reusable, meaning it's reused one after another. It's not concurrently usable. Two people can't share the same toilet. Don't try that at home. Okay? It also does not self-destruct after one uses it. Right? It's not like a potato chip. Once you eat it, it's eaten. Right? It's serially reusable. Usable by one user at a time, right? But you can have turn taking, right? One can use it after another, serially reusable. All right? So we have to have a serially reusable resource. There has to be no preemption. I can't be in a deadlock situation if there's a police officer that can take something from you and give it to you. Okay? If there is some management that exists where I can take a resource from one user and give it to another user to make things work, I'm not going to be in a deadlock situation because I'll exercise some level of preemption. I'll take it away from you and give it to you such that we can make progress. So I need to have serially reusable resources. No preemption. I can't beat the resource away from one user and give it to another. Okay? We have to have a situation where it's possible to hold a resource while waiting for another. Called hold and wait. Okay? This is a situation where I can hold a resource, right, while waiting for you to give me a resource. Unsurprisingly, the other condition is circular wait, such that I can hold a resource while waiting for a resource, and what can you do?
Wait for you to give me what I need so I can give you what you need.
Yeah, you can hold a resource while waiting for me to give you one. So now we have a cycle. So if we have serially reusable resources, no preemption, the ability to hold a resource while waiting for another, and have circular wait, we've satisfied the necessary and sufficient conditions, and therefore we're in a state of deadlock. Progress will never happen. I'm waiting for you, you're waiting for me, it's a cycle. There's nobody that's going to take your resource and give it to me, or take my resource and give it to you. Okay? So if we satisfy those four necessary and sufficient conditions, then we're in a situation where we're never, because of this dependency, we're never going to make progress. We're deadlocked. A live lock is sort of like a deadlock, except it's one that consumes resources. So the question is, when I'm waiting, what am I doing? If the answer is I'm on a wait queue, blocked, able to do nothing, that's one thing. If the answer is I'm sitting on a processor testing the condition, wasting processor time, that's another thing. If I'm blocked, that's simple deadlock. If I'm actually consuming a resource while I'm blocked, not only am I deadlocked, but I'm a special case of deadlock called live lock, meaning I'm using resources while deadlocked. Does that make sense? And this just depends how we wait. Okay, one way of waiting is I need this resource. I'm going to go sit over here until someone tells me I can have it. That's simple deadlock. The operating systems block that process. Taking me, put me on a wait queue. Live lock is, can I have it yet? 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 Right? Over and over and over and over and over again. Testing some condition. While not lock available. Okay. Okay, good enough. So we've talked about race conditions, where the outcome depends on which independent process happens to get to, or thread, or whatever your concurrency unit there happens to be, what their scheduling turns out to be. Deadlock is the case where progress can't be made because of these dependencies. Live lock is the situation we have deadlock, but we're burning resources in the process. Starvation is a slightly different issue. Starvation is the situation where, oftentimes because of priorities, somebody simply doesn't get a turn. You can imagine that, for example, the way printers, worked, let's say, purely hypothetically, is that the smallest job printed first. One-page jobs before two-page jobs before three-page jobs. Okay? Technique called shortest job first. This is a nice technique, actually, because it means if you're trying to print a one-page job, you can just go print your job and leave. Whereas if you're trying to print a 500-page job, life is sad, right? Because this is a big job. So you're going to have to wait no matter what. So if we stick a 500-page job before a one-page job, the 500-page job is still taking a long time. The one-page job is now also taking a long time. We agree? So That's not a good situation, right? Let's say we have a 500-page job, a one-page job, a one-page job, a one-page job, and a one-page job. How many tasks are now waiting for that 500-page job to finish? 1, 2, 3, 4, 5? What do you think? However many in the line. I think in my example there were 5, but maybe it was 4. Yeah, everybody's waiting for that 500-page job. If I reverse it, and I have a one-page job, 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 and a 500-page job, the one-page jobs go through pretty quickly, right? Almost no penalty. And the 500-page job, well, now it's really, it's getting penalized by a whopping 5 pages. Do you think they're going to notice? No, right? That's the argument in terms of shortest job first scheduling. Of course, the problem with this is there's a priority there, right? That means that if one-page jobs keep coming in, what happens to the 500-page job? Is it ever going to print? No, right? What's that? Well, the question is, they can do. You can have a lot of policies. Right? My proposal to you is if we actually have a shortest job first policy, this is actually what we do, right? It's possible for a large job to starve, never to get to go. Does that sound fair? No. Okay. So we talked about live lock. Starvation is the situation where, because of the priority system we choose to use, somebody never gets their turn. Does that make sense? And fairness gets at the same issue, okay? A scheduling system is fair if the prioritization has nothing to do with the requester or the request. But once I start looking at the requester and say, you're more important than you, I have a priority system. Okay? Dean's print jobs go before faculty print jobs. Priority system, right? That's not fair. Maybe useful, not fair. Right? So sometimes we intentionally unfair, right? It could also be, I don't know, have to do with the size of the job like we talked about. That's not a fair system. Nothing fair about that, right? Why should I wait just because my job is large? That's not fair. My job is important to me, right? So we have a whole bunch of things sort of wrapped up in this slide. Not all of them necessarily have to do with concurrency, but they're sort of classical problems a little bit. So races, the outcome depends upon which processor thread gets where first. Okay? Deadlock, the situation we have that circular wait so no one gets to go. Live lock, the situation where the deadlock isn't deadlock where I'm over in a corner sitting down waiting for a resource doing nothing on some block queue, but instead, can I have it yet? Can I have it yet? Can I have it yet? Okay? Starvation, because of our priority, somebody simply doesn't get a turn. Ever. They're starved. Starvation is a particular case of fairness, or lack of fairness. It's the extreme lack of fairness, where someone never gets to go. Concurrent programming is really hard. Most of it's not within the scope of 213, but fortunately some of it is. And so we'll talk about that today. Do you remember our iterative server? Think about the server side of that, right? Not the client side, but the server side of that. What did we do? We created a socket. We bound the socket to a port. We configured the listen queue. Everybody remember this? Then we started accepting connections. We accepted connections one at a time, right? I call accept returns a file descriptor. Now I have a session from that file descriptor between me and the client. I read the client's request, I process that request, and then I send my response. Loop back and do it again. Accept the next connection, read the request, process the request, write the reply, loop back and do it again. One at a time, right? Sequential, request after request after request after request. But now think about some pathogenic behavior. A client shows up, I accept the connection. Now what is it that I as the server am now expecting? Someone to talk to me. I'm expecting the client to do what? To make a request. What happens if the client doesn't make the request. What's that? I sit there twiddling my thumbs. Now, what about everybody else in line? What are they doing? They're watching me twiddle my thumbs. That would be nice if they could watch me twiddle my thumbs. Rather, they're just sitting there in line. They can't even see anything. No thumb twiddling show for them, right? This is called head of line blocking. I am at the head of the line. Everybody else is now, I got to the head of the line, right? Other people are behind me. Now I'm going to stand there at the head of the line and block. Okay? No one else gets to go. This is how denial of service attacks happen, right? You've heard that phrase, denial of service? Somebody shows up, they block, they get to the head of the line, they block, and now no one else gets to go. Now, this is really sad, right? Because I can have, if I write my server this way, I can have a system with a huge amount of memory, right? Tremendous memory throughput, 8 cores, 16 cores, right? And yet, because I wrote my code this way, in this iterative way, accept, read a request, process the request, write the reply, loop back and do it again, everybody's queuing up, and all of my resources are staying idle. This means I'm not using my resources on the system. This also means I'm subject to head-of-line blocking, denial of service attacks, all this type of thing. It'd be really nice if we could do something like this. Have the client show up, knock on the front door, accept that client, and allocate some resources to that client. And then have somebody else show up at the front door, right? Accept that client, allocate some resources to that client, and let those guys use their resources while we stand there and answer the front door. We're like the butler, right? Show up, answer the door, this way please, answer the door, this way please, everybody is off doing their thing. Now we can have concurrency, okay? And that's what we're going to talk about today, how to take our iterative web server and make it concurrent. Gain the ability to sit there and answer the door sequentially, but as soon as we do, send that work off so it can be handled in parallel. Make sense? Okay. And this is the example here of head of line blocking. All right? We go through, we connect, the server accepts, right? And then what's going on here? This whole time, the client's not doing anything. That's it. Server's tied up. Okay. I think we talked our way through that set of slides. Now, when it comes time to actually answer that door and dispatch that work in different directions to handle it concurrently, we have different tools we can use to do this. Okay? Processes, threads, and I/O multiplexing. And I think you guys have a fairly good sense as to what this is right now. Right? Processes. You guys have played with processes. How do we create a new process? What's that? I heard it from the back. Fork. Right? One thing we can do is we can fork a new worker every time someone shows up. Someone shows up, knocks on the door, we accept, we have a file descriptor, we fork a new process, right? It has a copy of that file descriptor talking to the same network socket. That's our worker child. That worker child goes off and deals with the work. Meanwhile, the server loops back and does it again. We also talked about what goes on in a fork, right? Fork does a lot of work, right? You generate a whole new process. That makes it robust but expensive. So today we're going to talk about threads, which are sort of like a lightweight version of processes. It gives us another thread of control, another schedulable unit of work, but it shares all of the process's resources. It shares the same memory context. It shares the same file descriptors. It shares the same signal handlers. It shares all of that. What it gets is a new stack. Because the stack keeps track of the function calls, right? The call chain. So since it has a new stack, it can go off and have its own life. And it has its own register instance. So every time we switch from one thread to another, we copy and save the registers. So we're going to talk about how to use threads. A third way we're not going to talk a lot about because it's a little painful and not really used very much anymore is I/O multiplexing. The idea there is we build a set of file descriptors. File descriptor 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we watch the set. Okay? And if any file descriptor changes, is readable, then we go deal with that one and we go back to watching the set. So it doesn't give us real concurrency in the sense of being able to attack multiple processors at the same time, being able to dispatch onto 3 or 4 processors. But what it does do is get rid of the head of the line problem. Because now everybody's at the head of the line. Does that make sense? Anybody who becomes readable can now be read. And so if in fact several of these connections become readable at the same time, several of these clients make the requests at the same time, I'm probably going to handle them in order from lowest to highest. I'm just going to loop through the things that are readable. But if number 10 becomes readable before number 0, no problem. I'm going to sit here in my select and my poll, wait around until something, anything becomes readable, and then walk through from lowest to highest and read from any client that's readable. And so if client 0, 1, 2, 3, 4, 5, they're not ready yet, they're not ripe, no problem. I'll just walk through and start at 6 then. So it's not really a form of concurrency, even though in 213 we talk about it that way. But what it does do is gives us some of the benefit of concurrency, lets us get past that head of line blocking. Okay? So we're going to talk about 1 and 2. We're not going to talk about 3, which is done via selector poll, but your book has a conversation about that if you're interested. And you can read about it there. Ah! What is that? Well, I know that's a Mackie. I was wondering who was doing stalking my class.
I just wanted to take the opportunity to see you in action and thank you personally for all the math majors and all the students at Carnegie Mellon. You served so well.
Good to see you.
Thank you.
Thank you.
Carry on and scare the shit out of him, Greg.
I thought you were going to stay for class.
I'm Mark Stelliglake. I have a line of 15 kids. Goodbye.
Have a great one.
Right.
Thank you. Okay. So what is this? It's got lines and dotted lines and dashes and a whole bunch of labels on it, like call and return and read and fork and write and I really should have read my slides before I came to class. All right, let's walk through this. I think we can do this. Okay. I can do this with a microphone too. Here we go. So what's going on? This in the middle is my server. On the left side I have client 1, on the right side I have client 2. So look at what the server is doing. It is accepting. Okay? That's the point where it takes a connection and does something with it. All right? Client 1 on the left, client 2 on the right. Each of these call connect. Okay? Normally, one would be accepted, the other would have to wait, right? What's going on here? Notice the fork. Ta-da! See the fork? This is going to handle one of the clients. We accept the connection, we fork, and we have a new client. Make sense? Meanwhile, this is now free. That accept returns, right? It's now free to handle another one. I can't get up to the top, but you can see we accept, right? And then we accept again. Accept, fork, accept. You guys see that? I come through, I accept one connection, I fork. That worker is now handling it. Now I loop back, I accept again, I fork again. I have a new worker that's now handling it. Make sense? What do you guys think? Okay. Code. So the iterative server, we know how this works, right? We accept, off we go. Now, let's look at how we do this concurrently. After we accept, we fork. We have the new process, right? The new process has the file descriptor from the old process, right? So now it goes off and handles it. This is the child. Okay? The child closes the copy of the file descriptor that was returned by socket. It's not going to be answering the front door, right? It's just talking to its one client. The fork child only needs the file descriptor returned by accept that lets it have a session. The server needs the one that answers the front door. So the client is going to close the socket file descriptor, and then it's going to do whatever it's going to do, and then it's going to close its own session. When it closes its own session, it goes away. Its job was to handle that one client. Okay. What about the server? The server does not need the file descriptor associated with the client, right? The main thread's job is just to answer the door. After it answers the door, it forks off a child. That child handles that session. So it closes the file descriptor associated with the session. We good? Okay. And that's the story. Of course, as we sit there and accept these connections, right, what are we doing? We're generating child after child after child after child. As they end, they're generating sig child after sig child after sig child, right? More importantly, they're generating zombies. So we need to have a signal handler, just like in our shell, to clean up the zombies. Okay. We need to make sure we reap those zombies. If we don't, we're going to have a memory leak, right? We're going to have a bunch of zombies building up. No one wants a world full of zombies. Same situation we have with the shell. Similarly, the main thread, right? It needs to close a copy of that session file descriptor. Because remember, think about our conversation about file I/O. It applies here, right? The file descriptor table, the open file table, the inodes. The inodes don't go away until the last file descriptor goes away, right? Because you have to get rid of the last file descriptor, decrement the count on the system-wide open file table entry to make that count go to 0, so that goes away, so it decreases the reference count on the inode, so that goes away. So if we don't close it in the parent, we're never going to be able to get rid of all those data structures. Pros and cons. Pros and cons. I hate pros and cons. Where's this, 3rd grade? What are the pros and cons of grilled cheese versus peanut butter for lunch? How about things we like and things we don't like about this? Things we like, it solves the problem. Right? It gives us concurrency. Things we don't like. Well, okay, it solves the problem. It's clean, right? We understand how it works. One process per client. Ta-da! Okay. We know what it means to share things, right? Via processes. It's simple and straightforward. What we don't like is it involves a big, heavyweight process. Right? There's a lot of overhead. And in general, I mean, it doesn't really matter as much in this particular example, but in general, right, if we have processes, it's hard to share between them. Processes are said to be protected, right? They have their own virtual memory. So if we want to share between processes, we need to do something like System 5 IPC, right? We need to map pages between 2 different sets of page tables. Okay. So another thing we could do are multiple threads. And I introduced threads earlier by saying that threads are sort of like lighter weight processes. They don't involve all the data structures. Okay? But they give us the concurrency, the scheduling ability, the encapsulation of the workflow. So threads basically have their own stack. So one thread of a process can call function A, then function B, then function C. Another can call function X, then function Y, then function Z. Okay? They can live their own lives. They live their own lives within the same process space. They share memory. If one of them opens a file, the other one has access to that file. Okay? If one of them segfaults, they both segfault. Right? Because it's the same process. The process seg fault. It's the process's memory that's been incorrectly accessed, right? They need to have their own registers, but that only makes some sense, right? The processor has registers. So when a thread is running on it, the thread is using those registers, right? You've seen assembly, you've seen the code the thread is running. It uses registers. So when I switch from one to another, I have to switch the registers. I have to go from your process's registers to your process's registers. So if I want to switch from you to you, I take the values of the registers and I save them to your stack. I then come over to your stack and I take the value from your registers and that I saved, and I read them back to the registers. Does that make sense? Make sense? Good? Okay. So that's the story. They get their own stack, they get their own registers. Now, if I have multiple processes, multiple threads, there's a little bit of a detail. Let's see if I can find the slide on it. I don't have the slide on it. Okay. So there's a little bit of a detail, right? The model we've talked about so far, the stack grows from top down, right? If I have two stacks, where are they? Or 3, 4, 5, 6, or 7, or 8, or 9, or 10, or 11. Yeah, what we basically have to do is to find a maximum stack size, and pardon the pun, but stack the stacks. Just stack, 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 where the stack has this much space allocated and can grow in it. Make sense? Make sense?
I don't like stacks.
You don't like stacks. Why don't you like stacks?
Stacks because when you stack them too much, they overflow.
Well, indeed, that is actually a problem, right? So the suggestion was, what happens if you have a stack that grows too big? Well, if I have a stack on top of a stack and one of them grows too big, it whites out the other. But that problem isn't unique, right? If I have one stack and it grows too big, it can grow down into the heap. Okay. So a process, right, contains one text area, one data area, right? But one stack per thread, which means that a single process can have multiple stacks. Make sense? Okay. When we think about process, we think about a hierarchy, a parent and multiple children, right? I'm the parent, I fork, now I have a child. It forks, now I have a grandchild. Parent, grandparent. Threads don't work that way. Threads are all peers. Okay? There's no difference. It doesn't matter whether thread A spawns thread B or thread B spawns thread A. They're all threads within the same process. They're all considered peers. There's no hierarchy among threads. I can have concurrency without having true parallelism. Okay? If I have multiple cores, this is great, right? Why is this great? One thread can run here, and one thread can run here. Okay? It's very easy to see how that happens. But I can have concurrency even if I have only one core. Because what happens is we interleave. Thread A runs for a while, then thread B, then thread A, then thread B, then thread A, then thread B. This type of interleaving, whether among processes or threads, is what allows your computer to be interactive the way it is. Right? That's how come it is that your instant messenger can go off while you're surfing the web, while you're also editing a document. Because there's this rapid turn-taking that happens. Okay? This time sharing. Okay? So what this means is that even if I only have one processor, if I have multiple threads, I can still have race conditions and deadlock and everything else. Because they can still take turns. I can still grab one of two resources I need, grab the left chopstick, And then it could be your turn, and you could grab the right chopstick. And now we each have one chopstick, and we both starve. Make sense? So if I have a multi-core machine, I can have, in this case, two things running at a time. There are two cores. A and B each can have their own core. B and C can each have their own core. A and C can have their core. Okay, over here, I only have one thing going on at a time, but A is still interrupted by B, and B is still interrupted by C, and C is still interrupted by A again, right? Does that make sense? So I can still have too many cooks in the kitchen. B and C can each add salt to A's cake. Okay. So we don't really have to be very concerned about whether the concurrency is the result of true parallelism or simply scheduler interleaving. Okay? What we have to be concerned with is whether or not we have concurrency. Because if we have concurrency, we have to worry about whether or not we have problems related to that scheduling. Threads and processes both provide this tool to allow these independently scheduled units of work. In many ways, they're very similar. Each has its own logical control flow, each can run concurrently, each is context switch. Meaning that concurrently can be either true parallel, one thread here, one process here, one process here, or it can be concurrency without parallelism, interleaving, context switching, switching from one to another. They're different, however, in their sharing model. Processes protect. Okay? You have your VM, you have your VM. Threads, they're all in the same process. They share the same virtual memory. They share the same file descriptor array. They share the same signal handlers. They share all of that. It's also the case that if you look at the time it takes to create a process and to reap it versus the time it takes to spawn a thread and to join it, the time overhead is about twice as great for processes. Okay? The POSIX thread interface, pthreads, is the standard way for creating, in managing threads. It has a whole bunch of function calls. We can create threads, which is sort of the equivalent of a spawn, of a fork. Okay? We can join threads, which is sort of the equivalent of a wait. We can find our own thread ID, which is the equivalent of get PID. We can exit ourselves. We can cancel a thread. And then we have some things for concurrency control. Turn taking. Synchronizing things. Here you see us creating a thread. Here you see us waiting for a thread. pthread create. Okay. The critical thing you see passed in is right here. That's the name of a function that serves as the main for the thread. Down here you can see our thread routine. Print hello world. So now we're going to create a thread, and this is going to be its main, basically. It's going to print out hello world and then end. So if you look at this, we have an integer, technically typed as pthread type, called the thread ID. We pass it in by reference, so we can write in the thread ID. We're typically not going to use any thread attributes. We pass in the name of the function that's going to serve as the body. And if it has arguments, we pass them in by reference. Okay? By default, there's one argument, which is a void pointer. The good news is that void pointer can be a pointer to a struct. And that struct can have a bunch of arguments. Okay? So this function is either going to take one argument. Well, this function is going to take one argument, whether it's one simple primitive argument like an integer, or a complex argument like a struct. That's how it's going to get its argument list. And so basically what we're going to do is inside here, we're going to cast this from a void pointer to whatever it is. Okay. So when we call pthread create, it creates the thread runs. In the meantime, over here, we're sitting in pthread join waiting for it. When it's done, we continue. Okay? So now you can see how this works. Okay? I come in, I accept, and I spawn a thread to handle it. But I have to be careful because there's a bit of a concurrency problem here. Okay? A little bit. Here's the thing. When I accept, I assign a file descriptor to a variable, right? Boom. Now, if I spawn a thread, if I fork, right, there's a new copy of that variable created in the new process, right? We agree? When we fork, it's a copy, so there's a new copy of that variable over here. So now each of us has our own. The client can go use that for its existing session, and the server can loop back, accept another connection, and reuse its variable. That copy is implicit in the fork. And then when that process goes away, throwing away that copy is implicit in ending the process. But with a thread, I'm not creating a new process. All threads share the same global state. So if I just had a variable, x equals accept, and then I said x equals accept, and then spawned a thread, you would take that and start talking to that client. I, meanwhile, would loop back and accept another client. And then I would spawn a new thread. And suddenly, you would both be talking to her. Right? Because as soon as I accept it again, that file descriptor would change from pointing to the original source to pointing to the new source. Does that make sense? Because it's the same variable. When I say x equals accept, I've now established a session. When I loop back and say x equals accept again, I've reassigned x. Since the threads are sharing that same state, they're now sharing that same variable. That's why I go through this trouble here to malloc a new variable and then use a new one each time. So now I malloc a variable and I accept, and you get that copy. Now I loop back and malloc it again and accept again, and you get that copy. And then I malloc again, accept again, and you get that copy. Does that make sense? What's the thing I'm not doing on this slide? I heard of it? Freeing it, right? I'm mallocing it for you and 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 even you. But I'm not freeing it. Better do that somewhere, huh? Here's where. Inside the thread, I have a pointer to that global file descriptor, right? The one I malloced. I copy it to a local variable because local variables are automatic. I don't have to remember to free them, right? And then as soon as I make that copy, I free my global one. Now I can't forget. So I allocate it before the accept, and I free it in the thread as soon as I make a local copy. Do I need that local copy? Technically, no. I could use the global copy and free it right before the return. There's nothing wrong with that. It just can complicate the universe. Because it means I have to remember to free it later on. It also means that if I end up with multiple paths, because there are errors and I return in different places, every one of those places I have to remember to free it. Much better to do it once at the top and then let local variables handle it automatically, right? Just makes the code easier. Okay. Yeah.
This would let you do a single instruction, multiple data, but what if you wanted to do multiple instruction, multiple data?
I'm not sure that I'm following. I'm sorry.
Like you've got one function that you're calling over and over again, the thread function.
Mm-hmm.
But what if you wanted to do different things on different threads?
Well, that's okay. If I want to do different things on different threads, I just have a different body. In this case, when I create that thread and I call pthread_create, I'm passing it a pointer to the same function. But if I wanted to, I could have an if statement or a switch statement or some other logical control there that caused a different body to be created for some of those threads. Does that answer your question? Okay. Okay. So we talked about this potential form of unintended sharing, right? This connection file descriptor and why it is that we malloc. All right. Now, I have a variable called I, which is local to main. Okay? But main is alive and well. Main, when main ends, the program ends, right? So now I go through and I create 100 threads. And to each thread, I pass a pointer to I. So you and 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 you all now point at the same I variable. Each of you is threads. Now increment that variable. What does that mean? At some level, it's I++. Okay? But what does I++ actually take? Load the value of I from memory into a register, increment the value of I, and store the value of I back. Move to register, increment, move back. Everybody agree? Okay. Now, imagine how this works with concurrency. If you read the value, and 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 now each of you has your own copy of the value. Now, each of you increments the value. You read 0, and you read 0, and you read 0, and you read 0, and you read 0. Now you each increment the 0 to 1. Now you each move the 1 back to the register. Do you see the problem? I intended to have 0 become 1, become 2, become 3, become 4, become 5, become 6, become 7, become 8. But instead, 0 became 1. I had 99 lost updates. And of course, anything is possible. It could work correctly where the scheduler doesn't happen to interleave. You load, update, store. You load, update, store. You load, update, store. You load, update, store. Your two could overlap and yours might not. So we could get any of a large number of values. Is this a race condition, deadlock, live lock, or a fairness issue? Race condition, right? What you see depends on what order things happen. Oh, and there it says race. So experimentally, right, if there's no race conditions, it would be perfect. The value would count its way from 0 to 100. If we run it on a single core laptop, it mostly is okay. Okay, but we occasionally miss things, right? We miss updates. Why? Because the scheduler happens to interleave it sometimes. On a multi-core laptop, right, it's wrong more than it's right. Because now they're actually happening in parallel. So a detached thread, if you're a thread and you detach yourself, that makes you like an independent thread, like the original main thread. That means no one needs to join you. Okay? When you die, your resources will just go away. Okay? It also means if main exits, you still live. Okay? So a default thread is a joinable thread, okay? Which means it can be reaped and killed by other threads, and if the main thread dies, it dies with it. But you can detach a thread, in which case it's now independent like the main thread. If the main thread goes away, your detached thread can still live. And just like main, if the detached thread goes away, it gets cleaned up. We need to be careful to avoid unintended sharing, right? And all functions must be thread safe. We'll talk about that next class. But the preview on this is if it's possible to have multiple things happen at the same time. Obviously, our code needs to be correct with respect to that, right? If I have a problem like we saw with that counter, my program's now broken. If I call a function that you wrote, that's part of a library that you wrote, or a library that you wrote, your libraries have to be correct. It's not enough for the code I see to be correct. All the code has to be correct. Yeah?
How are you defining correctness in terms of ordering of different threads or processes?
I'm defining correctness as doing what the programmer wants it to do, even in light of concurrency.
So view level as opposed to application concurrency.
So I think take 2 steps back. For right now, I'm defining correctness as if the code does what you as the programmer wanted it to do, then it's correct.
Okay.
If it does things that surprise you, then it's incorrect. So, you know, without getting into the details of views. So if my code is correct, look at my code, it's correct. I don't have any concurrency problems, you know, in my code. My code could still be broken if I call a function that's not thread safe. Right. So when we think about correctness, right, not only does the code we see have to be correct, all the code we call has to be correct. So in making library calls, if your code is threaded, you need to only call library calls that are thread safe. A lot of library calls aren't thread safe because they make use of static local state. Think of something like our network functions. right, that returned a pointer to a buffer that they had internally. Okay, like get host by name or something like that. Or string toke, where it keeps track of where you are in parsing a string. Right? Those are not thread safe because there's one buffer. It's a static local. Okay? So we'll talk about that in more detail next class. What do we like about thread-based designs? Easy to share. They're more efficient than processes. They have less overhead. What don't we like? Well, if we're all in the same process, right? If I overwrite a variable, right? If thread number 1, right, overwrites an array, it can overwrite some state that belongs to thread number 2 because they're within the same process. Does that make sense? Ah! That was fun. I wish we would have had a camera here. Next time we need a camera in front also, because the whole class should have seen that. All right. And this and that's a problem, right? Because it's hard to detect problems because if a thread has a problem and it's generating wrong results, or it's seg faults while it's running some thread's code, you're intently looking in that thread's flow of control at that part of the program for the problem. Whereas the problem might actually be that another thread at a completely different point in time that you're not even thinking about actually overwrote data. Really hard to debug. Never mind the fact that anytime we have concurrency, whether by threads or processes, that we have this interleaving, it gets really hard to debug because people think sequentially. People don't think concurrently. And so it's hard for us to force ourselves to do that. So again, we talked about processes. We talked about threads. I/O multiplexing we didn't talk about because it doesn't give you true concurrency anyway. It just lets you get past blocking problems. And it turns out to be just really tedious and really hard to get right. And so now that threads are very fully supported in most operating systems and most environments, we don't do a whole lot of stuff with poll and select. There's just not a lot of call for it. We're most of the time better off with threads. If we look at this from the perspective of the network manager, right, we can actually see that on the same port, we have more than one thing going on at the same time. We've accepted multiple connections on the same port. That's okay. It can keep track of it because they have different file descriptors, right? They're from different clients. A session is defined by a tuple of the client's endpoint and the server's endpoint. Each of these has a different client endpoint. Each of these is a different session, is a different connection, right? And the client endpoint is different every time. Does that make sense? Do you see how we can demultiplex these? Okay. So the TCP manager maintains separate stream for each connection. Each is represented to the application as a socket, but via file descriptor. New connections are directed to listening sockets. Data from clients is directed to one of the existing sockets. Any questions? You guys good? Okay, there's a small secret. We're working on getting some Saturday office hours. So if you need them, look at the webpage for them. Okay? We're expecting a zoo on Sunday for obvious reasons. Right? Because that's the last, people who use 2 late days will land on Sunday. So if you're counting on fast help Sunday night, understand that the staff is expecting a large queue. We're trying to upstaff it, but as it turns out, more students can show up and get in line than we have TAs. So you may want to consider getting it done on time, done with 1 late day, but if you're actually burning 2 late days, that's where we think most people are going to be, and so the office hours are going to be packed. That's our bet. Any questions? Have a great day, everybody.